Okay, let's go through step by step. This is a very important part and with a lot of points on any test I give you. The first part is the work energy theorem, where the change in potential energy of the spring comes from the work I put in. And so the work is the integral of force times dx, which we don't worry about. I don't tell you about that. I just tell you how far I compress it. Now when the spring expands, all of that potential energy turns into the kinetic energy of the bullet. You're conserving energy here. Momentum, yeah, you could say that the momentum that this gets is equal to the momentum, the impulse of the Earth, but the Earth is big. This is not part of the problem. How about any other lost energy, heat, etc.? Well, I say that the spring has no mass, so we don't worry about its motion, and it has no friction. So this is a complete energy transition. Now we smack into that mass, and we know in a collision, momentum is always conserved. So the momentum of the bullet is equal to the momentum of the bullet plus the block, because they move as one body together. The kinetic energy of the final block and bullet together came from this kinetic energy, but a huge amount was lost as heat. Remember, in a collision, in an inelastic collision where they stick together, a lot of kinetic energy turns to heat, as we showed when I made those two cards come together and stop. All of the kinetic energy turned to heat. And so ultimately, this kinetic energy that this has turns to potential energy as it swings up to a higher elevation. And so we'd like to be able to say that the potential energy of the spring is equal to the final potential energy, the gravitational potential energy, of the bullet plus the block. But we can't do that because a huge amount of energy is lost as heat. Yeah, and if you did that and solved it, you'd wind up with a height of 25 meters. Probably not realistic. And so we see we can't say this because so much energy is lost in heat. What you have to do is find the energy you put into it, which winds up being 500 joules. Set that potential energy equal to the kinetic energy of the bullet, and you get a velocity of the bullet about 70 meters per second. Here, you conserve momentum. The mass goes up by a factor of 100. In order for momentum to be the same, the velocity is going to get less by a factor of 100. And you end up with 0.7 meters per second. This thing isn't moving very fast. And then you can conserve energy as that kinetic energy of this block, much less than the original kinetic energy of the bullet, turns to potential energy, and you end up with 25 centimeters. But that's not how I did it, actually. What I did was I said, how much of the kinetic energy did I lose? So I remember that kinetic energy is equal to 1/2 mv squared, but I can write it as p squared over 2m. And one thing I know is this momentum is equal to this momentum. So the momentum part is the same, but the mass goes up by a factor of 100. So in fact, the kinetic energy, because the momentum is the same before and after, but the mass is 100 times as big, the kinetic energy of the pendulum is equal to 1/100th the kinetic energy of the bullet. So the kinetic energy after the collision of the pendulum is 1/100th the initial kinetic energy of the bullet. So you can see we can make this inequality an equality if we recognize that we've lost 99%. And so the final potential energy of this block is equal to 1/100th the original potential energy in the spring. And we add that 1/100th, and we add that 1/100th. And yes, this 25 meters becomes 25 centimeters.